secret to all life in the universe right there. All right. So there's still another way to add water across a double bond, anti-Markovnikov hydroboration. So let's do that. So, what's the product of that reaction right there? That's the product. So if you're working on this, do an anti-Markovnikov addition of water across the alkyne first. So there's your anti-Markovnikov addition of water. OH on the less substituted carbon, H on the more substituted carbon. That is actually, no that's not. That wouldn't be the product of step one, sorry. That would be the product of step one. Okay, so now what step two does, and again, you're not required to know the mechanism for hydroboration. So I'm kind of just waving my hands here and saying what happens. What step two starts to do is it replaces the carbon-boron bond with a carbon-oxygen bond. And so that's what you get after the peroxide does its bit with the boron. This is an enol, right? Carbon-carbon double bond, single bond to OH. So this is an enol. And then just like over there, if you make an enol, the keto form is going to be more stable. And the way to judge this, the keto form is always going to be, so when you have a carbon-carbon double bond, that's your ene. Carbon-oxygen single bond is the ol, so that has to be bonded to it. Okay, so this would not be an enol. Right? There's an alkene and there's an alcohol, but it's not one group. They're not in contact. All right, so the way you're going to convert this, again, I'm going to go through the mechanism for doing this under basic conditions in just a second, but just to see it, the carbon-oxygen single bond will become a double bond, the carbon-carbon double bond will become a single bond. Really what you're doing is you're moving an H from the O to the alpha carbon. All right, so let's do this under basic conditions. It's a little different than the mechanism under acidic conditions. Remember, we got aqueous hydroxide here. Okay, so the hydroxide takes the OH proton. This gives something called an enolate in water. Right, it's an enolate because you pull the proton off of an enol. So like a carboxylic acid, if you pull that proton off, you get a carboxylate. So enolate. Here we have a resonance structure. Looks like this, and you can get to that resonance structure by pushing these arrows. So the O minus will make a pi bond, carbon-oxygen pi bond, carbon-carbon pi bond then puts a lone pair on that carbon. And then got water in there, so the negatively charged carbon takes a proton from water. Right, so again, 2 steps. And I've said this over and over and over. If you do a reaction under acidic conditions, if you're writing a mechanism for a reaction that happens when there's a strong acid present, you can't make a strong base. So you're never going to have hydroxide or methoxide with a strong acid. Under basic conditions, on the other hand, you're never going to have a strong acid. So we can't have any H3O+. Water is not going to take this proton. If water takes that proton, I generate H3O+. All right, so it's got to be a pretty strong base. It sounds like a simple thing, right? Like basic conditions, you make bases and you make weak acids and bases and strong bases. Under acidic conditions, you make weak acids and bases and strong acids. It's easy enough to put in your head, but then you have to recognize what's a strong acid, what's a strong base. That can trip people up. The other way you could do this mechanism straight from here would be make that pi bond and grab the H there, right? So remember, resonance structures are the same molecule. So it's not correct to use one of those resonance structures in the mechanism and not the other. Same over here. You could use this resonance structure, you could use that resonance structure. Doesn't matter. They're the same thing. Questions about that?
When does it form like the aldehyde? Because wasn't that what you had in the PowerPoint show?
Yeah, so I just haven't drawn the H in.
Oh, okay. So that is an aldehyde.
Yep.
Okay.
And again, this reaction especially, but really any time you add water across an alkyne, you really need it to be either a terminal alkyne or have one of the carbons super sterically bulky or really able to stabilize the positive charge. Right, if you imagine just doing either of these reactions with, right, if I do that, you get both of those enols, right? Secondary cation, they're basically the same. So you'll get 2 different enols, which means you'd get 2 different ketones. There's no way to separate that. So neither of these are real good reactions if the alkyne isn't really unsymmetric. This is an unsymmetric alkyne, but not enough to make one cation better than the other. Other questions about alkyne chemistry in general, I guess, at this point. All right. Okay. So you've pretty much seen everything that's going to be on exam 2 at this point. Exam 3. You've definitely seen everything that's going to be on exam 2. That'd be funny, right? So here's this thing from exam 2 that I didn't show you until now. You've seen all the material that's going to be on exam 3. Here in this question, I'm asking you to come up, this is a synthesis problem, I'm asking you to come up with a series of reactions that would give us this epoxide from that alkane. So, you guys have your notes, you have your book. You can't get close to each other, but you can talk to each other. I'm going to pause the machine here. Maybe. How do I pause?